Hello, everyone. Thanks for joining my presentation. My name is Kang Pyo. I'm going to talk about the innovative material for the nuclear system. So the title is the one-dimensional nanotubes as an effective defect sink in the metallic exhibit greatly reduced radiation damage. Topic is a little bit long, but I'm going to explain what does the mean reducing the radiation damage. So currently the renewable energy is very big concern because the development is very slow, but the climate changes rapidly occurs. At the same time, the global population required more energy because the global population is growing more and more. So as a consequence, we need some substitute energy source. So the nuclear energy could be the one of the option, especially fusion nuclear power plant. At the same time, now fusion power plant also rapidly developing. So this nuclear power plant could be the option to lead to develop the renewable energy, and also it could be the future energy source. But the problem is the nuclear power plant, the material issue limit their performance. So one of the problems is under the radiation environment, the material absorb the neutron and generate vacancy and void. Once they combine each other, then they can form this void, and also interstitial can make a sort of cluster. So in this case, the material, their structure is changes. For example, material, the geometry is become larger, so volume expands. So because of this void swelling, in macro scale, material become bigger. The size of the material become bigger. In this case, all the distortion occurs. In addition to that, if this void swelling occurs, then material suddenly become very brittle under the nuclear environment, and just 10% of void swelling lead to 0% of ductility, which means there's no tolerance of any structural deformation. And in addition to that, especially for fusion power plant, the N alpha transmutation generate the alpha particle, which is the helium, and helium started to accumulate in the material, and eventually it make the material like brittle, and then it can easily fail. So then what would be the solution to outgassing helium and then stop the swelling? We want to propose to fill 1D nanodisperser, so the inside the metal, which can act as a straw to suck out the helium, and also improve the radiation tolerance along with the mechanical properties, and then creep resistance. So we developed the new process through the surface diffusion cold welding at the nanoscale. We incorporate carbon nanotube inside the material, especially inside the grain, and then we can do further shaping process. For example, extrusion. Extrusion is one of the example, but we can do rolling and other casting, even 3D printing. So this is the mechanical properties. The tensile strength, this is SS curve. The tensile strength, as we increase the carbon nanotube concentration, goes higher. But what we can focus is this non-uniform deformation. Typically, if we increase the strength, then the fracture strain degrades. But because carbon nanotube provides special function, so it actually stop propagating the crack and also notch. So carbon nanotube can contribute to extend the non-uniform deformation, which eventually lead to extend the fracture strain. So basically, the carbon nanotube can increase the Young's modulus, yield strength, and tensile strength, and then fracture strength. So all mechanical properties can enhance by the carbon nanotube incorporation. Carbon nanotube, unlike a 0D particle, they are very long, so it won't allow the diffusive dislocation climbing at high temperature. So this data shows that the carbon nanotube, by adding carbon nanotube, is a strain function of time, shows the deformation process is really long. So if we plot this one into the strain rate, then we can see the 1% of carbon nanotube, their minimum strain rate is 1,000 times extended than that of control aluminum. So so far the material property is very promising. Then how about the radiation tolerance? This is the just direct comparison that the helium ion irradiation on the control pure aluminum and the aluminum carbon nanotube composite. We can see the pure aluminum, there are much bubble generated after irradiation, but the control aluminum, the addition of carbon nanotube just 0.58%. We don't see any void swelling, of course. Also, we did a self-ion irradiation to stimulate the neutron irradiation. It's the same like a carbon nanotube can provide interface, so they can the generated interstitial vacancies. They can easily recombine, so we don't see any cavities. But the control aluminum, we can see lots of cavities. We want to see the extreme helium implantation. What happens if we apply the high concentration of the helium in the aluminum? So approximately about 70%, which is the 40 years of the reactor core life. We can see in the control aluminum there are many bubbles generated, and in the surface we can see the cracks because of the volume expansion. But carbon nanotube, the volume expansion is much suppressed compared to the control aluminum, because carbon nanotube can act as the nano chimney, so that it can outgas the helium. So the void swelling and the generation of the helium bubble is much suppressed compared to the control aluminum. In order to see the damage mechanism in the carbon nanotube composite, we use the in situ irradiation. So we use the IVEM, which can do both the TEM observation and then in situ irradiation. So this is the area of the carbon nanotube, and we can see the defect is migrate toward carbon nanotube, and they disappear. So carbon nanotube can provide their interfaces, and then this interfaces is a completely good venue to recombine all the defects, such as the vacancy interstitial. Even it can also outgas in the helium. So this is the statistic data shows that the control aluminum, when we irradiate, then we can see the black dot, the density of black dot and size of black dot is high, whereas the carbon nanotube sample, there's not much the defect generated after irradiation. Even the developed defect also annihilated. This is the volume fraction of the defect as a function of the dPa. The control aluminum, in the control aluminum, volume fraction of defect goes higher and higher as we do irradiation. However, the aluminum carbon nanotube, it can easily saturate. Even later stage, the volume fraction of defect even decreases. So this is another statistics. The control aluminum, we can see the particle size getting larger and larger, whereas the carbon nanotube sample, the initial size actually slightly increases but decreases, which is the clear demonstration of the defect recombination, and also major fraction of the defect decreases more and more as we do irradiation, which is corresponding to our previous in situ observation. Even simulation shows the similar same phenomena, that carbon nanotube sample can easily saturate the number of defects because they can they provide interface and annihilate each other. We did an experiment for aluminum, but we are now working on the other metals such as zirconium. Zirconium is very important for the nuclear power plant because it can be used in the it is used in the fuel cladding, and we did the same experiment, and then we found the carbon nanotube in the grain, and we can see the void swelling is much suppressed by adding carbon nanotube, and then from the XF experiment we can see the less concentration of interstitial in the carbon nanotube zirconium composite. And also the hardness shows the embrittlement of the the matrix is much suppressed by adding carbon nanotubes. So basically, our idea works for the zirconium as well. And what happened to if we do extreme irradiation? So we irradiate something like a 72 dPa. And what we found that carbon nanotube are still 1D structure, and some of carbon nanotube is kind of merged each other. But at least most of carbon nanotube is still like a 1D hollow structure, and it can also act as the defect sink. And this Raman shows the carbon nanotube after irradiation, they turn into the tetragonal amorphous carbon. And also, if we irradiate with a high energy ion, then the carbon nanotube turn into the carbide. But the carbide also is a 1D structure. We can see like fossa of the carbon nanotube, about like 10 nanometer diameter. And this carbon is 1D aluminum carbide can still act as the as the defect sink. So even if there's phase transformation happens, still it doesn't violate our previous observation. It also plays the same role. And the when we see about the mechanism, the carbon nanotube doesn't have any like cutting mechanism. So the mechanical properties can be high, and also at the higher temperature, it resists any kind of deformation. So this mechanism is special compared to the other precipitation and also other 0D particle. Now we are going to test nickel CNT, and we're going to test the zirconium CNT. Even later we want to produce ton scale. So this carbon nanotube metal composite or 1D nanowire metal composite idea works for different types of material. So this is all my presentation. Thanks for your participation. Thanks for listening to this talk.